Hello, everyone. Welcome to the Spectral Geometry and the Cloud seminar. Today, we have the pleasure of having Badreddine Benhellal, who will speak about curvature contribution to the essential spectrum of Dirac operators with critical shell interactions. Badreddine, the floor is yours.
Okay, thanks. Well, first of all, I would like to thank the organizers, especially John for the invitation. And thank you all for being here and listening to me, especially at that moment. So this is a joint work with Konstantin Pankrashkin, who is actually my postdoc supervisor here in Oldenburg. And as you can see here, I mean, the title is kind of summary of the talk. So I'm going to speak about critical shell interaction for Dirac operator. I will be mainly interested on computing the essential spectrum of this operator. So let's start. Okay, so there we have some acknowledgement for the German Research Foundation that's going on. So in this talk, I will consider Dirac operator in R3. So throughout the talk, I will assume that the mass M is strictly positive, and free Dirac operator in R3 that I denote by H0 is given by this expression. That is a matrix valued differential operator. It acts on component of function, which are in H1. So in this definition, we have alphas and betas. So alpha is alpha 1, alpha 2, and alpha 3. Those are usual Dirac matrices written down here. So the beta here, we have the identity E2 minus the identity E2 here. And the alpha are composed by so-called Pauli matrices written down here. And the notation here, alpha dot or sigma dot in the following, means that for X in R3, we are taking kind of a scalar product here. So in the end, so this is the full expression in the matrix form of this free Dirac operator. So in the diagonal, as I said, we have the mass. Here we have the change of sign because of this minus here. And the partial derivative are in the anti-diagonal. Okay. It is well known that, as the name suggests, this is came from the Dirac equation, which describes the evolution of spin 1/2 particle from quantum mechanics. So here we have some well-known facts. So the first thing is that this free Dirac operator defined on H1 is self-adjoint, and its spectrum is purely continuous, and it is the union of these two intervals. So, say in the physical sense, so this interval is the positive energy, and this one is the negative energy. And the second point is that when we take the product of H0 minus Z with H0 plus Z, then we get this Helmholtz operator. So, for example, if you take Z is equal to 0, this means that this Dirac operator is somehow a local version of a square root of this Helmholtz operator. But unfortunately, I mean, we need to pay the price of working with the matrix valued version here. And because of this identity, we have, say, an explicit expression for the resolvent of this Dirac operator in terms of convolution integral, where here phi z is this fundamental solution of H0 minus Z. So remark that here we have, say, fundamental solution of this Helmholtz operator, and we are just applying H0 plus Z to get this fundamental solution. So those are the basic things to know about, say, the Dirac operator in R3. So let's move to the perturbed operator that we are interested on. So in this talk, omega will be a bounded and smooth domain in R3, and we set omega minus be the complement and sigma the common boundary. Okay, and I'm denoting by nu normal vector field on sigma. So here we have the picture. So our main goal is to study this perturbed Dirac operator that I'm denoting by H in L2 of R3. So here we have the imperturbed operator H0 plus this delta potential. Okay, so this is the Dirac distribution supported on the surface sigma. The parameter epsilon and mu are real valued. Okay, and epsilon here is the strength of the electrostatic shell interaction, and the mu is the strength of Lorentz scalar shell interaction. Okay, so this is kind of classification of potential. This operator, in fact, is kind of an idealized model. So, in fact, the real model that physicists, I guess, they are interested on is the case of strongly localized potential. That is, in fact, think about localized potential near the boundary, so not supported on surface, but near the boundary. So, and this is a kind of limit when we shrink those potential. In fact, there is some paper where this is justified. So the story of the study of this Dirac operator is long and goes back to a paper by Dietrich, Exner, and Siba. I'm going to discuss a bit more about the literature later on. So the first thing to do is to give a meaning for this Dirac distribution and define this operator a certain domain. So the question we ask is self-adjointness and on which domain, and what can we say about the structure of the spectrum? Okay, so first, let me give you, say, a simple definition for this Hamiltonian. There is another equivalent definition that I prefer more, because somehow there we can see all the protagonists that are involved in study of this model. If I have time later, so in the end, I can show you the this equivalent definition. But for the moment, let us pick a function u. I'm writing u plus and u minus. So here I'm identifying somehow L2 of R3 with L2 in omega plus, direct sum with L2 of omega minus. So here we take function in H1, and we define the Dirac distribution as usual. So we take the mean value, and so I keep here u plus and u minus for the trace on the boundary. Okay, that's for simplification. And now, in fact, if it is not too hard, I mean, to check in the sense of distribution that the action of this perturbed operator on such function u is equal to this one. So here we have the action of free Dirac operator inside domain omega plus, here the action inside the omega minus, okay? And then we will have a boundary term, so something which lives on the boundary. So this is the term which comes from, say, the Dirac distribution, and this one comes from the action of free Dirac operator. So in order to ensure that this guy is including L2 of R3, so we need that this quantity must vanish on the boundary. I notice that somehow we have both u plus and u minus, and this is called the transmission condition. So this suggests to define our operator on the following domain. So we pick a function in this Sobolev space, and we ask this boundary condition to be satisfied in H1 half. Okay, and our operator, as I said, will act in the sense of distribution like this. All right, so in fact, with this definition, okay, one can show that for any parameter, any combination of the parameter, the domain of H is a dense subspace of L2 of R3, and H is symmetric on that domain. And this means, in particular, that with this definition, H is closable. And in fact, one can show more. And for that, let us first introduce this Dirac superspace. In fact, this is the maximal domain for the Dirac operator. Recall that multiplication by beta is bounded in L2. In fact, this is a Hilbert space. And moreover, it was shown by Ormière-Bonafou and Biga that in the case of smooth domain, the trace of function phi in this domain is in fact in h minus 1/2. Okay, and we can show that actually the domain of the adjoint is a set of function which belongs to this Dirac subspace. But however, here the transmission condition that we had before must be satisfied in h minus 1/2. All right. Okay, as I said, in fact, I mean, story about this shell interaction for Dirac operator is long. But say in the study, there is two particular case. So the first one, which is called non-critical, we see why it is not critical. So the definition. And in fact, in this situation, we can show that our operator is self-adjoint. Okay. So on first paper dealing with this kind of perturbation was, I mean, this paper by Dietrich, Ixner, and Shiba, where in fact they studied the case of sphere in R3, followed by this paper by Shabandi Viabandi, where they got more result about spectral property. So I mean, you can see, I mean, the date here, okay, and then we have a kind of jump. So we took, I mean, time to deal with more general, say, geometries, and this was done by a series of paper by Arida Balaga, Mas, and Biga, using some harmonic analysis techniques and some extension theory, and followed also by papers by Bernd, Hixner, Holzmann, Lutorishik, where they are more involved in, say, on techniques on the extension of symmetric operators, namely the boundary triple techniques. Okay, so here all those paper mostly deals with more general surfaces, and there would be, I mean, more advanced on the study of those kind of perturbation. And I would like to cite also, I mean, this paper by Albert Mas and Fabio Pizzichillo, where they showed this kind of convergence when you shrink strongly localized potential. So in fact, almost all these papers say deals with the purely electrostatic case, so where mu here is equal to 0. And there is this paper by Holzmann, Ormière-Bonafou, and Pankrashkin, where say they got many information about the point spectrum in the case of the purely Lorentz scalar case. Okay, in fact, why it is not critical? So let's see what can we say about spectral property. In fact, if we assume that our domain omega plus is kind of Holder domains, say with gamma strictly bigger than 1/2, and this in order to ensure that this trace of function in Dirac subspace are actually in h minus 1/2, and assuming that we are under this condition, then we have self-adjointness of our operator, and the essential spectrum is characterized as the one of 3 Dirac operator. Okay, and moreover, say the discrete spectrum in the gap minus m is finite. Okay, so let me say just a few words about these 2 points. Okay, so let's start, I mean, with the first one. Okay, so in fact, we have always the inclusion of these 2 intervals in the essential spectrum, because when you assume that omega plus is bounded, then omega minus is unbounded, and you can always, I mean, construct basic ones to prove this the inclusion of these 2 intervals in the essential spectrum. But in fact, to prove the reverse or just the equality, like there is, it was proved that there is a Crane resolvent type formula, And with this resolving formula, we can show that the difference between these two resolvents is compact, and hence we get this characterization. And and second point here, to prove that spectrum is finite inside the gap, this is follows because of this Sobolev regularity. So we have H1 Sobolev regularity, and in fact, whenever you have a Sobolev regularity, okay, under say at least Lipschitz condition on the surface, we can always show that inside the gap spectrum is finite. So remember this: whenever we have Sobolev regularity of any order S strictly bigger than 0, we will have just a finite spectrum in the gap. And we combine this remark with some min-max principle in order to show this result. So in the end of the day, in fact, in this situation, okay, so in fact, perturbation by this delta potential is just compact. Okay, so this is why it is not critical. And in fact, some of these points still, in fact, remain valid if we assume Lipschitz smoothness on the domain omega plus, but under some smallness assumption or under some size assumption on these two parameters. But so let's now move to so-called critical case. So the case where epsilon square minus mu square is equal to 4. So in this situation, say for C2 smooth domain, it was shown for the purely electrostatic case by Ormière, Bonafont, Vega, Bernd, and Hosman, that in fact, the restriction of this operator in H1 is essentially self-adjoint. Okay, so it is self-adjoint in L2. However, the domain is not included in any Sobolev space. So remember what I said just before. Okay, so I said if we have any Sobolev regularity, then we would have just finite spectrum in the gap. So here we start, say something stranger. And in fact, this model has, say, a natural two-dimensional analog, which was studied by Bernd, Hosman, Ormière, Bonafont, and Pankrashkin, where they showed self-adjointness for any combination of these two parameters. I'm going to say more about this paper. So, in fact, during my thesis, I showed the following. So, if we assume that omega plus is C2 smooth domain or just local deformation of hyperplane, so in this situation, omega minus and omega plus will be unbounded domain, and under this condition, our operator is essentially self-adjoint, and the closure is given by this. So we still have here transmission condition in H-1/2. Okay. So because of the absence of Sobolev regularity, so one may think that, of course, we should have something in the gap. We should have essential spectrum in the gap, or say an infinite sequence of eigenvalue that say converge to plus or minus m. And in fact, there is some situation where we showed that in fact we have essential spectrum. So let us start from some well-known result. So assume for the moment that epsilon is equal to plus or minus 2, and we take a Lorentz scalar parameter is equal to 0. Then in the case of hyperplane, okay, it was shown by Aretabarara, Mas, and Vega that 0 is an eigenvalue with infinite multiplicity. Okay, and then it was shown by Bernd and Holzmann that in the case of compact C2 smooth surface, if we assume that there is a flat part with surface measure strictly positive, then 0 is in the essential spectrum. Okay, so there is a difference between this critical case and non-critical case. Okay, and in fact, I showed the following. So in the case of locally deformed half space, we have a full characterization of the essential spectrum. Okay, and then we still have this the union of these two intervals, and then we have an extra point which is in the gap. And we can play with this parameter epsilon mu so that we can achieve any point inside the gap. Okay. And in fact, I was motivated by this result proved before by, as I said, by Bernd, Holzmann, Ormier, Bonafont, and Pankrashkin, where in the 2D case, they obtained, in fact, a complete characterization when they take sigma being C-infinity closed smooth curve. Okay. In fact, they get exactly the same essential spectrum. All right. So up to now, so one may ask, what happens for general compact surface, at least in smooth case? So before I state our main result, I would like to mention a result that appeared 1 week before ours by Bernd, Holzmann, and their student. In fact, they showed, again, under this condition, in R3, of course, we have always this point in the essential spectrum. Okay, so, right, so we have always this point in the essential spectrum. So we can ask, do we have this same characterization for general compact surface? Well, I mean, the answer is no. So, in fact, we showed with Konstantin the following result. So denote by kappa 1 and kappa 2 the principal curvature of the surface, and denote by a sigma the maximum of this difference. Then the essential spectrum of the closure of our operator is characterized by this union. So again here, as I said, these two intervals are always in the essential spectrum. But here the novelty is the following: is that we have a full interval inside the gap. Okay, so this interval is centered at this point that appeared already before. Okay, and has this length. So, and this length is characterized by this difference of principal curvature. So let me just do a couple of remarks. Notice that we have this equality if and only if sigma is the union of finite and many disjoint sphere. Because in fact, it is one known result from differential geometry that the only surface for which we have the equality for the principal curvature is the sphere. Okay, and moreover, notice that we can always, I mean, manage to have a surface such that this quantity blow-ups, and therefore we can always find a surface such that the essential spectrum is full real line. Okay, but and then we have an open problem, which is the following. So we are looking for surface with genius bigger or equal to 1 and fixed area that minimize this maximum. Okay. In fact, as far as I know, in fact, I don't know if we can write this problem in Lagrangian form. And as we see in this remark, so using a lower bound proved for the Wilmore energy, this one, okay, which is actually achieved by theory of revolution. And using this Gauss-Bonnet theorem, so we end up with this lower bound where key here is the Euler characteristic. But this bound is somehow never achieved, okay? And it is far from being sharp. So actually we don't know even if there is a minimizer for this problem. So as I said, minimizing this, in fact, so would minimize a smaller essential spectrum for genius bigger or equal to 1. Okay, so if you have any question, you may ask. I mean, otherwise, I'm going to devote the rest of the talk for the proof. Okay.
So I would have a quick question. So you say that this lower bound is very far from being sharp. is it easy to see that it is, or?
In fact, here in this, to get this lower bound, we use this one. So, and this one is achieved by the Torah of revolution. Okay, so, and you can, in fact, we know that for this inequality, this is, if this one is achieved for someone, then we would have equality here also. And this is false, of course.
Yeah, but the inequality could still be sharp, but just be a strict inequality instead of being in the large, right? In the sense that, do you think that we should be able to get a larger constant?
Yeah, I would say yes. Yeah.
Okay.
In fact, we can see, in fact, that for the Torah of revolution, I mean, this is, I mean, there is kind of Torah of revolution where, I mean, we can get a better bound, in fact. So I can continue. All right, so let's start the proof. In fact, in order to show, in fact, we show, in fact, a better result somehow. We show the following. There exists a symmetric zero-order pseudo-differential operator with such that we have this equality. Okay, so this is kind of Birnbaum-Schwinger principle. Okay, so we have our operator. Sorry, here it should be the closure. So our operator, it acts on the whole space, and this operator acts on the boundary. Okay, and in fact, this essential spectrum of this operator is exactly the new interval that appears in the for this operator. Okay, so we are going to reduce the problem from the whole space and catch this operator on the boundary using pseudo-differential operators. Okay, so let me just recall the fundamental solution here for lambda between minus m and m. Okay, so let me present, I mean, first protagonist in this story. So let us define this Cauchy operator associated with H0 minus lambda. This operator defined in this principal value sense. So it acts from the boundary to the boundary. So this Cauchy operator, in fact, is a classical, I mean, object from harmonic analysis, and the story about the boundedness of these guys and existence is so long and goes back to Calderon, Zygmunt, David and Sams, and finally a theorem by David and Journey, where they show, I mean, a general result. So in fact, this limit exists almost everywhere, and our operator is bounded in L2. This is shown, say, in Lipschitz case by Arredabara, Mas, and Bega in this context. And they showed also that this Cauchy operator is self-adjoint, and we have this, say, algebraic identity, which plays actually an important role in the analysis of shell interaction. Okay, so before I give the link between this Cauchy operator and the operator H, so let me just recap some history of this operator. In fact, the boundedness of this Cauchy operator, say, under some doubling condition of the surface, characterize kind of surface, which are called uniformly rectifiable. This is just a generalization of Lipschitz graphs. Okay, so in this sense, somehow you can open any paper, say, on shell interaction for Dirac operator. Say first thing, I mean, that you ask is that this operator is bounded. Okay, in this sense, in fact, we can study somehow. This is the largest class of surface on which we can study this kind of problem. And another result, which is also, I mean, useful in the proof, for example, of self-adjointness of this Dirac operator with shell interaction in Lipschitz case, is the following. So if you for Lipschitz surface sigma, which are compact, in fact, we have these inequalities. So what we are saying here is that, so here, this symbol, well, here sigma should be alpha, sorry for that. So we say here that the distance of this anticommutator, okay, to the set of compact operator is comparable to the distance of the normal to the set of vanishing mean oscillation function on the boundary, okay? So in fact, it is known that for Lipschitz surface, having the normal in VMO, this characterize, say, subset, a class of domain, we do not have corners, okay? So the compactness of this operator is equivalent to the absence of corners on your surface. So this class of domain is in between Lipschitz and C1. So it is bigger than C1, okay? But it do not have corners, okay? Anyway, so the last point is that this Cauchy operator in context of C infinity smooth surface is in fact a zero order pseudo-differential operator and has many applications, for example, in the study of point-characteristic law of maps for Dirac operators on the domain. So there are many links relating this this Cauchy operator with Dirac operators in general. Okay, but to state, I mean, important links that were needed here in this context, let us denote by delta sigma non-negative Laplace Beltrami operator and set L tilde this resolvent of Laplace Beltrami operator. Well, I mean, it is well known that Laplace Beltrami operator is a pseudo-differential operator, okay, and also that L tilde is an isomorphism between HS and HS minus 1/2, and this is for any S. And now we define this operator L lambda. So here we have the multiplication by this Laplace Beltrami operator. So in sense of pseudo, this and this gives you first order pseudo-differential operator. And here inside we have this Cauchy operator, which is zero order. And recall that here we have just, I mean, constant matrix. And notice that we are in the critical case, meaning that 4 is equal to epsilon square minus mu square. So in other words, in fact, this is the inverse of epsilon plus mu beta. Okay, so this operator acts on this maximal domain, and it is classical result that this operator is essentially self-adjoint on this domain. And in fact, we have more. So for any lambda in the gap, this operator is self-adjoint. But moreover, we have this characterization of the essential spectrum, which says the following. So we have lambda in the essential spectrum of H, if and only if 0 is in the essential spectrum of L lambda. So this is our first reduction to the boundary. Okay, so now the goal is to study the essential spectrum of this operator. Okay, so to do so, remember that our fundamental solution has a matrix structure. Okay, so we can write it as follows. So here we have K lambda, okay, which is just a fundamental solution of the Helmholtz operator. And then we have this part in the diagonal, which comes from the singular part. So, and then we can define, say, the trace of the single layer potential, which acts on a function in L2 of sigma. And this matrix valued operator, which is defined again in the sense of principal value. So with the help of these two guys, which are in fact self-adjoint because of self-adjointness of the Cauchy operator and bounded also, we may write this Cauchy operator in this matrix form. So in the diagonal, we have the single layer, and here we have the tensor product with the identity. And in the anti-diagonal, we have this singular integral operator. All right, so in order to study, I mean, this L, we need first, I mean, to study the property of this operator k lambda and w lambda. So in this sense, we have obtained the following result on pseudo-differential property. Well, for k lambda, this is somehow known and classical. So the result says the following. So k lambda is positive pseudo and of order -1. So, and it is an isomorphism between HS and HS -1. So the W is a zero order pseudo-differential operator. But finally, we have this point, which is for us the most important. So we have these equalities modulo an operator of order -2. So here, remember, k lambda is acts on scalar function. So here this is 1, and here on a 2x2, this is a 2x2 matrix. So this is why we have this, and this is here. So for this, so the first equality is somehow not hard, I mean, to see, but the second one is is not obvious. Okay, so this is the most important property. Sorry. Okay. And because of this property, we can define this square root, which is positive, and it is an isomorphism from HS to HS -1/2. Okay. And therefore, this multiplication is an isomorphism between HS and itself. So recall here, this is the definition of L tilde. So with the help of this isomorphism, we can simplify our operator L lambda. Okay, so I'm denoting by L lambda tilde this operator. So I'm multiplying somehow to get out this Laplace-Beltrami operator, and we have this equivalence. And remember, this is equivalent to have lambda in the essential spectrum of closure of H. Okay, and here we have the block structure of L lambda tilde. Okay, so recall that this is somehow the inverse of k lambda, so we will have simplification inside. And in order to study the essential spectrum of this, there is a well-known technique to reduce somehow the problem from 4x4 matrix to a 2x2 matrix, and this is the Schur complement actually. So now we are going to study the Schur complement of L lambda tilde. Let me just recall that this algebraic identity with this block structure simplifies as follows. So we have this identity relating k lambda and w lambda. And note also that when you take lambda is equal to plus or minus m, and the following, I'm always going to take m. So we will have this operator square is equal to -1/4. Okay. And in fact, now, in the argument that I'm going to show you now, somehow in the computation, we can take lambda is equal to m. Okay, so for simplification, I'm going to take from now lambda is equal to m. Yes, that is, I mean, for L, W, and K, I'm going to take lambda is equal to m. Then my operator lambda tilde, okay, will have this form modulo, say, an operator which is symmetric and of order -1. Okay, so and Schur complement, which is defined in the following sense, okay, says the following thing. So when you have a block structure like this, if you can somehow invert one of this corner in the diagonal, okay, then you can define under some condition on the domain of this corner and this one, the Schur complement. And now notice that because lambda is in the gap, so this is always a positive. And because of this criticality, epsilon square minus mu square is equal to 4. So epsilon minus mu and epsilon plus mu have the same sign. Okay, so in the following, I will assume that epsilon minus mu is positive. Okay, just to simplify things. So in this situation, this corner will be invertible from L2 to H1. Okay, otherwise we can invert this corner. So we assume that this is the invertible operator. Then the Schur complement is equal to this corner plus the product of these corners and in between we have the inverse of this upper left corner. Okay, and in fact there is a result saying that 0 is in the essential spectrum of Schur complement if and only if it is 0 is in the essential spectrum of L lambda tilde. And I'm recalling here the equivalence that we had before. So here we are reducing our problem from the whole space to the study of 2 by 2 valued integral operators on the surface. Okay, so now we are going to simplify this Schur complement using this iterated resolving formula. Okay, so we plug this formula in this one, then we get the following. Okay, what we get here. So our Schur complement is equal to something plus a pseudo-differential operator of order -1, which is symmetric. And from here, I mean, we see, I mean, the point that appeared before here. So minus mu should come from here. Okay. All right. So in fact, somehow using this property that I stated before, okay, then one can write this difference as follows. Okay. So this would be equal to sigma nu times this anticommutator, then we will have Wm. So in the end, I'm denoting here by A this anticommutator. And in fact, this anticommutator is somehow an analog of the Kerzmanstein operator in this setting. I mean, in setting of this Pauli algebra. Okay, and it is a classical object from complex analysis. And thanks to the pseudo-differential property of Wm, that in fact I didn't write the complete result, but we have in fact the explicit symbol. Okay, and in fact when you see the explicit symbol, it is easy to verify that A is in fact a pseudo of order -1. So in fact our operator S lambda is bounded in L2. So here Lm will give a contribution, so will be, I mean, a pseudo-differential operator of order 1, and this one is of order -1. So so the power will cancel, and in the end we'll get, I mean, a bounded operator. So what I'm saying is that in fact we have the following from this formula. So remember that we had this reduction. So I'm taking out here the closure for the Schur complement. And then we have our operator in the boundary. So here we have now lambda in the essential spectrum of this operator. Okay, and this is the operator P that I stated in the beginning of the proof. So now our goal is to compute the essential spectrum of this operator. Okay, and to do that, so we choose somehow a nice local coordinate to simplify the computation as follows. So we pick a point on the boundary, and we denote by mx the Weingarten map. And recall that the eigenvalue of the Weingarten map are the principal curvature. And then we choose a basis for an orthonormal basis for the tangent plane, so that those vector would be eigenvectors for the Weingarten map associated to each principal curvature. And so that E1, E2, and the normal vector field is an orthonormal basis for R3, which is positively oriented. So in this context, then we can construct a local chart so that we have this property, okay? And then our theorem in this situation is the following. In fact, as I said before, A is of order -1 and P is of order 0, and their principal symbol in this local coordinate chart are given by the following. So for the Kerzmanstein operator, we have this equality here. So, and we see here the difference between the curvature. Okay, so in fact, the curvatures come from the symbol of Kirchner-Stein operator. And then for our operator P, we have a full symbol here. So here we have the curvature term, and here we have the center of this interval. And in fact, we can compute for each x and xi, of course, fixed, that in fact the eigenvalue of this symbol are given by this two eigenvalues. Okay, and then there is a classical theorem to compute essential spectrum of a zero-order classical pseudo-differential operator. In fact, what you take the image with respect to x, and then you take the union with respect to xi. So in the end of the day, the essential spectrum of our operator P is equal to this interval that appeared in the main result. All right, so let me just give you some quick point on the proof from where this curvature comes. So recall that our, say, Kirchner-Stein operator have this integral form. In fact, we can take out this principal value because it is bounded, and it is of order -1 actually. Where here this kernel is given by this formula. So here we have sigma n wm plus wm sigma n, okay, sigma nu. And then you use this Clifford relation. So here, I mean, when you multiply x and y in this setting, you get the scalar product plus this this product of x and y. Okay, this is the wedge product. Okay, and this is true for x and y in R3. So with this formula, we can simplify this this kernel. So, and what we get is the following. So we will have a first term here, okay? And in this first term, what we have is exactly, say, the kernel of the double layer minus the kernel of its adjoint. So in the sense of pseudo-differential operator, we know that so the double layer and its adjoint are pseudo-differential operator of order -1, okay? And in fact, they have the same principal symbol. So with this minus, so the principal symbol of the difference will cancel. So we'll have something which is which has order -2. So in the calculus we may forget about this. So this is of order -2, and then the principal term comes from this one. Okay, and in fact, using this special local coordinate and using Taylor formula, okay, one can see immediately from where it came this curvature terms, okay? And I don't know if I still have time or so. This is somehow the end of the proof. I'm not going to say
yes, you have time. You still have 10 minutes if you want.
Well, if I have time, I would like to show you the other definition, because somehow, okay, we start from an operator on the whole space, and I guess the most important thing is from where this operator, from where this Cauchy operator comes, and from where this L lambda comes. So let me just explain this very quickly. Okay, in fact, recall that phi lambda is the fundamental solution of H0 minus lambda. So here lambda is equal to 0. Okay, then I can define this integral operator. So this is in fact somehow the single layer for the Dirac operator. So it takes a function from the boundary and it gives you something which lives on the whole and whole space. And it is shown by Arizabala, Amat, and Biga that this operator is bounded from L2 to L2 of R3. Okay, and it is shown by Ormier, Bonafo, Viga, Bernd, and Holzmann that this map, in fact, extends continuously to a bounded operator from H-1/2 to this Dirac Sobolev space. Remember that this Dirac Sobolev space is the maximal domain for the Dirac operator. And in fact, we have this jump formula for the trace. Here, what I'm denoting, so I'm taking the restriction of this map on omega plus and minus, and then I take the trace. Okay, So in fact, when you take the trace of this map, then you get the Cauchy operator. So here C denote C lambda with lambda is equal to 0. So the Cauchy operator comes from this jump formula. All right. And then if I denote by lambda this operator, okay, remember in the definition of L lambda, we have this kind of operator. And in fact, the domain of the closure writes as follows. So we'll have a regular part, which is in H1 for the free Dirac operator, and then a singular part with G in H minus 1/2. Okay, and in fact, we can show, if you, for example, take the restriction of this function to omega plus and to omega minus, and you iterate, I mean, the computation we did in the beginning in order to get transmission condition. And in fact, our transmission condition is equivalent to the following. So here I'm taking the trace of U, which is defined in H1 of R3. So we check just the trace on the boundary, is equal to minus lambda of the singular part, G, okay? And our operator, in fact, will act in the sense of distribution as follows. So it will act as free Dirac operator on the regular part. And this is for any phi in the domain of the closure, all right? And here, the only way to give the meaning for the Dirac distribution is by taking the mean value, okay? So, and then in fact, to see the relation between L and this closure, so we regularize here our function G. So here I'm taking G in L2, okay? And here I'm applying this Laplace-Beltrami operator. So in the end here, in fact, this function, sorry, here should be G. So L tilde applied to G is something which lives in H minus 1/2 according to this definition. Okay, and then I'm regularizing also this transmission condition. So here we get the condition that L tilde of U is in L2, and then we have our operator L lambda with lambda equal to 0. So this is in fact the relation. And one can also, for example, instead of taking phi of 0, we may take phi of lambda and then change a bit this function on this domain, and we will get all those L lambda operators. So this is in fact the link. And in the sense of boundary triple theory, in fact, you have the following. And in fact, you have self-adjointness, equivalence between self-adjointness of H and this L lambda defined on some specific domain, say, for example, H1 instead of L2. Well, I think I'm going to stop here, and thank you for your attention.
Thank you very much for the talk. We now have time for questions. So please, if you have a question, just unmute yourself and go ahead and ask your questions. Does anyone have a question or a comment? No, so I have a very generic question. So could you tell us what you're planning to do next with this?
Well, I mean, next point is to generalize this for higher dimension. I mean, this is, I guess, the most important question. Well, I mean, it's not clear how to do it because somehow now in higher dimension, you need to be careful on keeping the structure of the operators. And also you need to use somehow the Clifford algebra. So here we have, I mean, explicit formulas, but in higher dimension, things becomes more complicated somehow.
Thank you. Anyone else wants to ask something? If not, let's thank the speaker again. Thank you very much.